Answer for question 1A. For Roman 1, resonant peak magnitude MR equals to 7 dB. Resonant peak frequency omega R equals to 9.5 radian per second. For Roman 2, I got the bandwidth from the negative 3 dB. Thus, the bandwidth is equals to 15 radian per second. For Roman 3, I got the cut-off rate slope is negative 40 dB. Next, question 1B. The question gives GS equals to KS plus 50 over S square plus 15S plus 100. Then, I minimize the quadratic pole and the simple 0, and I got the 0.02S plus 1 over S 0.1 square plus 1.5 times 0.1 plus 1. Then I calculate each gain K and the magnitude equals to 20 log K equals to 20 log 1, 0 dB. For number 2, pole at origin, I got the cut-off frequency at 0 radian per second because the slope must be at negative 20 dB. And number 3, simple 0. From 0.02 S plus 1, the cut-off frequency is equals to 1 over T equals to 1 over 0.02 equals to 50 radian per second. And lastly, quadratic pole. I use the quadratic equation, which is the omega n square plus 2 zeta omega n plus 1. And I calculate the omega n, which is the square root omega n square equals to square root 100, and I got the omega n equals to 10. Then I calculate the cut-off frequency for quadratic pole, which is 1 over T equals to 1 over 1 over 10 equals to 10 radian per second. This is the dot plot that I did. For the first line, which is the blue line, I do it for the gain, and it is a straight 0 dB. For the orange line, which is the pole at origin, I start from 20 dB and then ends at negative 60 dB. The cut-off frequency is at each 10 radian per second. Next, the quadratic pole. I start from the 0 dB, and starting from the cut-off frequency of 10 radian per second, I start to go lower at the negative 60 dB. The quadratic pole is the green line. For the sum, which is the final line, the color is olive, or which is starting from 20 dB, and then it goes down until the negative 60 dB. This is the magnitude diagram. For the phase diagram, I start the gain from the 0 degree, and it is a straight line until the end. For the orange line, which is the pole at origin, I start from the negative 90 degree, and then it is a straight line, which is or a flat line. And then simple 0, it is starting from 0 degree, and at the cut-off frequency of 5 radian per second, the line start to shift upward until the 500 radian per second, which is 19 degree. And then it goes to the flat line at the 90 degree E. And then the final line is negative 90 degree for the answer of, for the sum or the final line. I start from the negative 90 degree and then goes to flat line until the cut-off frequency of 10 radian per second. And then it goes down to 5 radian per second, which is between negative 135 degree and negative 180 degree. And then it goes down at negative 170 degree. And then it goes down again at 50 radian per second. And then it goes down again at 10 radian per second. 150 radian per second goes down to 50 radian per second. And then it goes down more to at cut-off frequency of 10 radian per second, 100 radian per second. And then it shifts upward to 500 radian per second at negative 80 degree. And then it goes to the flat line at the 1000 radian per second, which is at the negative 80 degree. Question 1C. For Roman 1, the question asks to get the gain margin and phase margin and then whether it's stable or not and the reason. For the gain margin, I got equals to 0 minus negative 37 equals to 37 dB. And the phase margin equals to negative 90 degree minus negative 180 degree, and I get positive 90 degree. The closed loop system is stable because both gain margin value and the phase margin value are both positive. For Roman 2, the pitch or the slightly light pink color from the dot plot of the magnitude diagram, I can say that the system become less stable. Gain margin shift upwards because the gain increase, which is K equals to 20 dB, and curse the gain margin to decrease.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nani Devina binti Najmi, and I will present question number 2. I will explain the Bode plot and stability analysis for unity feedback control system. So the given transfer function is GS K S plus 10 S S squared plus 8x plus 25, where the gain, which is K, is 40 over 25. Make the gain in decibel is 4.082 at 1 rad per second. So next, identify the poles and the zero. There is one pole at the origin and a second order pole with a natural frequency of 5 radian per second and 0 at 10 rad per second. Because of the pole at the origin, the initial slope of the magnitude plot is minus 20 dB. And then at 5 radian per second, the second order poles reduce the slope by another 40 dB per decade, then giving a total slope of minus 60 dB per decade. And then at 10 radian per second, the zero increased the slope by 20 dB per decade. Then so the final slope become minus 40 dB per decade. Then the frequency where the magnitude cross 0 dB is called the gain crossover frequency. For the phase plot, the pole at the origin contribute minus 90 degree. Then the two poles contribute at additional minus 180 degrees. While the zero at plus 90 degree. As a result, the phase starts at minus 90 degrees and gradually decrease. Then finally settling near minus 180 degrees at high frequency. Then the frequency where the phase crosses minus 180 degrees is known as the phase crossover frequency. So from the Bode plot, both the gain margin and the phase margin are positive, which means the closed loop is stable. Then the bandwidth is 0.15. So approximate equal to the gain crossover frequency, which is 0.15. Then if the gain is increased by 30 dB, the magnitude plot shift upward while the phase plot remains unchanged, so causing the phase margin become negative, so the system not stable anymore. It's become unstable.
My name is Liwan Yi and my matrix number is 2311515571. Today, I will explain question 3, which focus on Nyquist stability analysis. Looking at figure 3.1, system S2 is more stable than system S1 because its locus is further away from the critical point -1 J0, meaning it has better gain and phase margin. Both systems are type 1, having one integrator because the plot starts from infinity at a phase of -90 degree as frequency approaches 0. In part B, we have the transfer function Gs Hs equal to 10 over s power of 2 plus 2s plus 5 by substituting s equal to j omega. We find that at omega equal to 0, the plot starts at the real axis point 2, 0. As omega increases to infinity, the magnitude goes to 0 and the phase approaches -180 degree. For part C, since the open loop system has no poles in the right half plane and the Nyquist plot does not encircle the -1 J0 point, the closed loop system. Finally, in part D, if we add an integrator, the system becomes Gs Hs equal to 10 times s power of 2 plus 2 s plus 5. This adds a constant -90 degree phase lag. The Nyquist curve shifts clockwise, moving closer to the critical point. Therefore, the stability margin decreases, making the system less stable or even potentially unstable.
Hi everyone, my name is Lu Ziyan. I would like to discuss about question 4. For question A1, system 1 has one integrator because the plot approaches infinity along the negative imaginary axis as omega equal to 0. A single integrator is the only component that provides a constant -90 degree phase shift and infinite magnitude at low frequencies. For system 2 has two integrator. The plot approaches infinity along the negative real axis. Two integrators provide a total phase shift of -180 degree. For question 2, the system 2 has better stability because the system 1 passes much closer to the critical point -1 than system 2. The system 2 crosses the negative real axis much further to the left of the critical parts, indicating a larger gain margins. The system 1 passes inside the unit circle very close to the critical points, indicating a very small phase margin. To plot the Nyquist plot, first we set the s equal to j omega for Ls first, then we find out the magnitude and phase for Ls. Next, we set the omega equal to 0 to obtain the low frequency characteristic at omega equal to 0. So we get 1 over 3 in 0 degree, and next we set the omega equal to infinity to obtain the high frequency characteristics. Then we get 0 but in -180 degree. Next, we rationalize the Ls by multiply the conjugates, and then we find the real axis crossings by using imaginary parts equal to 0, and we get the omega equal to 0. Next, we find the imaginary axis crossings. We use the real part equal to 0, and we get the omega equal to square root 3. And we find when we sub the square root 3 into the magnitude of the system. So we get the crossing point is equal to 0.2887. Next, we find the gain margins. Then we sub the A equal to 0, and then we get the gain margin is infinity. Now we can plot the Nyquist plot by and label all the value we get. The closed loop system is stable because the Nyquist plot does not encycle point -1. The points only cross the real axis at omega equal to infinity. Since there is no other crossings, the gain margin is equal to infinity. The phase margin is positive since the plot stays far from -1. Next, for D, when integrator is adding to the forward path of the system, the closed loop system is stable, but less stable than in question B because the adding an integrator introduced an additional -90-degree phase shift, and there is no encirclement of -1s, but the plot passes very close to -1s. The gain margin and phase margin also decreases. For E, when a 0 at S equal to -2 is added to the systems, the system stability is increases because a 0 in the left half plane provide a phase lead. This pull the Nyquist plot away from the critical point -1s and towards the right half of the complex planes. This result in an increased phase margin and improve the transient response, making the system more stable.